Going to show my age again. I'm old. My parents are older. My mother turned 83 last week. One of my mother's favorite things are musicals. Lots of song and dance, right? Fred Astaire and Ginger Rogers, Gene Kelly, and lots of people. But one of the things that we always had a discussion about was who was the best dancer? Fred Astaire or Ginger Rogers? Well, the interesting thing, that Ginger Rogers did everything Fred Astaire did. Backwards in high heels. We're going backwards. We have spent a very long time taking derivatives. What if I know how fast something is changing? That's something I can measure. I can look at the level of the water in the reservoir and see it's gone down or gone up. I can look at the rate of change. How do I get back the original function? How do I go backwards, backwards, backwards? It's a joke, people. It's a joke. Capital F of x is an antiderivative for little f of x if, when I take the derivative of capital F of x, I get f of x on some interval. Doesn't have to be everywhere, just on some intervals. We'll discuss why we need an interval later. Nice, easy example. If I tell you, here's my derivative, it's 3x squared. What's the original equation? X to the third would work that, right? We take 3, bring it down in front. We take 3, we subtract 1 from the power. That gives us the 2. Oh, so capital F of x is x cubed. But wait, there's more. Mean value theorem. I need to go back to the mean value theorem. Beginning of this chapter. What did we discuss with the mean value theorem about derivatives? I had to put a star next to it. Find it in your notes. That's not what we actually said with the mean value. Because there's an important word in that definition up there. F of x is an antiderivative, not the antiderivative. There's more than one. The mean value theorem if I have two functions that have the same derivative, then what? One of the very last things I wrote on the day we did mean value theorem. Jordan? X cubed is an antiderivative for 3x squared. And that means that any other function that is also going to have the derivative 3x squared cannot be different from x cubed by anything other than a constant. So I could also say add any number I want to the end of that x cubed. And all of those, when you take the derivative of any of those, what do you get? The same damn thing. Because the derivative of a constant is 0. If I asked you to graph these 4 functions, what would you see on your screen? Which? Graph them. You have a calculator. You don't have to take my word for it. Do the graph. The only difference between the graph of f and the graph of these 3 g's is a vertical shift. This one's moved up 1 unit. This one's moved down 7 units. This one's moved up, I don't know, a little less than 2 units. They all look effectively the same. They have the same slope at every point. These are parallel curves, not parallel lines, but parallel curves. Page 357, figure 1. They're the same curve, just moved up and down. Which means, in spite of the fact that I said an antiderivative up top, I can actually claim a general idea. A general antiderivative is just written with a plus c at the end. I don't know what that constant is. That will depend on the situation I'm looking at. But in general, I'm just going to put a plus c. We'll figure it out later. So the general antiderivative for sine of x. What's something whose derivative is sine x? On my formula sheet, it says derivative of cosine is minus sine. But under the minus here, so I have to have the minus here. But wait, there's more. Really? Thank you. No, that's e to the x. My horrible handwriting again. Advantage number one, just like with the trig one at the top, I have that table that's attached to the exam of inverse trigs and trigs. So I may not always remember them, but I can look them up. What's something whose derivative is 1 over 1 plus x squared? My inverse tangent. Almost. My first reaction is to say that k of x should be ln of x. But here's an interesting point. 1 over x is defined as long as x is not 0. Yes? ln of x is defined. What happened to my other side? What, I pissed it away today? I can't lose that other side, and we did check this when we were learning the chain rule. We said, hey, if you put it on the left side, you can't take the ln of a negative, but if you took the absolute value, you'd make the number positive. The absolute value of a negative number is the same as multiplying by -1. So if x is negative, take the ln of minus x, that works. And I get 1 over minus x, and then the chain rule, that gives me a 1 over x also. So I need to realize that when I'm doing 1 over x, it could be on either side. I want my antiderivative to work on either side. So I'm going to put a little star here and say, really, I should be doing the absolute value, because I need an interval. And the interval, in this case, is everything except 0. Should be all the numbers bigger and all the numbers less than to make the domains agree with each other. We are often looking for the largest possible domain we can get when we do an antiderivative. Questions? I did 3x squared earlier. If I go to do the antiderivative of just x squared, my brain says, well, in order to get the square here when I take a derivative, I should have started with a power that's 1 bigger, right, with an x cubed. Because when you take a derivative, you subtract 1 from the power. So I should have an x cubed in the antiderivative. But when you take the derivative of x cubed, you get 3x squared, and that's not what I have. Right, the 3 would go here. I need something that's going to cancel that 3. What's going to cancel that 3 is a 1/3. Because now when I bring down the 3, it'll cancel out. Aha. Let's generalize. Let's suppose I had any number up there. Well, the thing I need to start with when I take the derivative has to have a higher power. And since I subtract 1, it should be 1 bigger. But again, if I go to take the derivative, this number is going to come down in front. It's not there. I had to have canceled it with something. I have to cancel it with 1 over this new number. I think this one's a little important. When is it broken? When does that fail? But if n plus 1 is 0, then what's n? And isn't that 1 over x? X to the negative 1? By the way, this tells me something really deep and hiding in my polynomial behavior. This polynomial rule idea here, this power rule, that's what we call it for derivatives, that's what we call it for antiderivatives. This power rule works except when x is minus 1. And that's the one that gives me a logarithm. So there's something deeply connected between logarithms and powers, and I want to figure out what that is eventually. Not now. Page 358, the box in the text. Please notice, there's my power rule. There's my exception to it. There's e to the x. This is for some other base other than e, just like the derivative formula on the top of our formula sheet. Cosine, sine, secant, secant. These are all on the formula sheet. We didn't do hyperbolics. I'm not worried about those last two. It's just these two up here. These three, 1, 2, 3, are the only three you need to have memorized. Everything else is on our formula sheet. This one, power rule, logarithm, the exponential. The rest of them come off our trig formula sheet. That's correct. But then there were those first two rules. The first two things that were listed there said that when I had a constant times a function, we did this with derivatives. If I'm going to take the derivative, what do I do with that constant out front? I just leave it there. So the same thing is true with the antiderivative. And if I am adding or subtracting, and I do the antiderivative, I just add or subtract. Hold that thought. We're not there yet at all. Later. Don't rush me. Start with the easy stuff. But this means I can put these together. But I will tell you right now, in advance, that two things I do not see anywhere in that list on page 358 are the product rule and quotient rule. Working those backwards is harder. The rules were more complicated when I took the derivatives. Their antiderivatives are going to be equally complicated. We'll put that off for now. Which means this second part here, I don't want to use the quotient. How can I fix that if I don't want to use the quotient rule? I'm sorry, person? If I make it x to the minus 1, I can move it up, right? Okay. Product rule wasn't on there either, so I'm still kind of twitchy about this. But it's not a bad place to start. It's just not finished yet. I can't take my antiderivative the way this is written either. Say again? Factor. Factor means pulling stuff out. Let's multiply it in. If I multiply this in, if I distribute this across this set of parentheses, well then 2x to the fifth times x to the minus 1. What do you do with the powers? You add them. What power of x is that? Fractional powers come from roots. That's x to the 1/2. So when I add those powers, I get x to the minus 1/2. Now I can do the power rule on the second and third terms, and I know that the antiderivative for the trig piece off my formula sheet. The antiderivative sign, just wrote it down. So the 4 is going to stay there, and I'm going to get minus cosine of x. Now, I'm going to be sneaky for a minute. There should be a plus c on each of these bits, right? A plus c here, and a plus c here, and a plus c here. Those are 3 different numbers. Just add them all together and call it one big number and put it on the end. Here, the 2 stays, and I get 1/5 x to the 5th. And here, negative 1/2 plus 1. Yes, but I'm doing the antiderivative. Going the other way. And the derivative minus cosine is what gives me sine. So I got to go the other way. Negative 1/2 plus 1 is positive 1/2. So I get 1 over 1/2 x to the 1/2. And then on the very end, a big plus c. You can simplify this a little. And x to the 1/2 is the square root. 1 over 1/2, take the fraction out of the bottom and flip it over. You don't have to, unless the situation calls for it. Just like with taking our derivatives, we're only going to simplify where we absolutely have to. Questions? This is an example of a differential equation. I gave you the derivative, and you gave me the original function. There are lots and lots and lots of different strategies for working with different kinds of differential equations. And differential equations are some of the most commonly used models for real situations in mechanics, engineering, chemistry, biology. They're the way we figure out how things change over time most often. But the situation I just gave you, where I gave you the derivative, you gave me the antiderivative, is missing something. Because there are infinitely many possible solutions to the problem we gave because of this. If I were to give you an additional piece of information, then we could use that to find a particular solution, a value for that C. For example, here is the additional piece of information. Find f of x so that f prime is this given function, e to the x plus 20 times the quantity x squared plus 1 to the negative 1, and f of 0 is negative 2. This extra piece of information is called an initial value or a boundary value, sometimes initial condition or boundary condition. And it's what's allowing us to solve for a particular solution to our differential equation rather than just a general solution. So the first thing I need to do is to figure out my general antiderivative, and then I can solve for the C value that came out of that. This piece I'm okay with. This piece? What the? I'm very limited in the things I am absolutely sure I know what the antiderivatives are. And I'm looking at my formula sheet an awful lot. And stuff to a power is nowhere on there. I have no idea what that is, and no, not in this case at all. But I can do algebra. Negative 1 power means goes in the bottom. Okay, wait a second. I saw something very similar to that just a couple minutes ago. Sorry? Because that was 1 over 1 plus x squared, right? But nobody cares what order you add in. So this is the same thing as e to the x plus 21 over 1 plus x squared. And now I can say exactly that is the derivative of my inverse tangent. So f of x, what's the antiderivative of e to the x? Yay! And the antiderivative of 1 over 1 plus x squared is the tangent inverse of x. And then my plus c. This is the general antiderivative. But I want to be more specific. I want a particular antiderivative. I want the one who's got a y-intercept of negative 2. Because that's what that value is. It's f of 0. And f of 0 is the y-intercept of my graph. So I'm telling you, you have all these parallel curves to pick from. I want the one that goes through this spot. F of 0 is what happens when I put in 0. So put in 0. And I should get out negative 2. Fortunately for me, I have a calculator with a tangent inverse button, but I should be able to remember what's an angle whose tangent is 0. 0 itself. But e to the 0 is 1. And that means that c is equal to -3. And our particular antiderivative, or our particular solution, has our constant in it. Questions? We can do this more than once. This time, instead of giving you the first derivative, I'm giving you the second derivative. And instead of giving you one condition, I'm giving you two. Now, because these two conditions happen at two different x values, we're going to call these boundary conditions more often than initial conditions. Initial conditions all happen at the same x. Boundary conditions happen at different x's. Technical detail, if you never remember that, that's fine. It's a 4 on the end. I want to get from f double prime to f. I'm going to take this antiderivative process twice instead of once. When I do the antiderivative of f double prime, I'm going to get f prime. So f prime of x is the x squared becomes x cubed over 3. I need the 1 over the new power, and I add 1 to the power. That's my power rule. I wrote it as 1/3 x cubed. If you write it this way, that's perfectly fine. That's the same thing. Plus antiderivative of x. What power of x is that? That's the first power, so it should become the second power. The 6 stays there, and I get x squared over 2. Wait a minute. What power of x is on this 4? There isn't any, right? That's a 0th power, which means I'm going to get a first power. Plus c. And then we can simplify this. 4x cubed plus 3x squared minus 4x plus c. I am being a little pedantic here in writing out this version. I don't want to do the multiplications and divisions in my head until I'm really good at doing the antiderivative rules. But if you go directly from here to here, because you've done the divide by 3 and the divide by 2 mentally, that's fine. As long as you do it right. If the number changes and I don't know what the change is, I'm going to have a problem. I cannot figure out what this C is at this point in time because none of my conditions are about F prime. I know it's a number. I have no idea what number it is. And I can't solve for it yet. I need to get to F. So do me an antiderivative one more time. When I do the x cubed, the antiderivative is going to give me an x to the fourth over 4. There's a 4 in front. It's going to cancel out. When I do the antiderivative of the x squared, I'm going to get x cubed over 3. There's a 3 in front. It's going to cancel out. When I do the antiderivative of x, I get x squared over 2. There's a 4 out front. 4 over 2 is 2. C is a number. Just like the 4, that's got an x to the 0 on it, so it's going to get an x to the 1. I would prefer not to. At this point, I need to add another constant, and I don't want to use C again because then I think, oh, they're the same letter. They got to be the same number. They don't have to be the same number. They need to be something else. You could call it anything else you want, but it's another constant. D, K, Q, Fred, George, I don't care. Smiley face, whatever label you want. But now I can go back to my boundary conditions and I can plug in. And depending on which x I plug in, I'll get expressions that have C and D and numbers in them. And I'll be able to solve for C and D. What was my first boundary condition? F of 0 equals 4. So that means if I put in 0 here, 0 to the fourth plus 0 cubed minus 2 times 0 squared plus C times 0 plus D equals 4. Notice that everything except D disappears. And I get D equals 4. If I put in the next boundary condition, I can use this in that boundary condition. F of 1 equals 1. 1 to the fourth plus 1 cubed minus 2 times 1 squared plus, I don't know C, so C times 1 plus D has got to be equal to 1. One raised to any power is a 1, so this is 1 plus 1 minus 2 plus 1 plus 4, no, not 1, that's a C times a 1, equals 1. So what's C? This 2 cancels with this 2. I move that to the other side. I get C equals 1 minus 4 is negative 3. Which means I now have my particular equation. X to the fourth plus x cubed minus 2x squared minus 3x plus 4. It worked. I could even do this without any sort of formulas at all. I could draw pictures. Remember, we took a graph and looked at the slope and said, oh, the slope here is positive, so I'm going to put a positive dot. The slope here is negative. I'll put a negative dot. I can go backwards. Do exactly the same thing in reverse. Page 360. Here's my slope. The slope is a negative number. It starts out really negative and gets less negative. The graph of capital F has a negative slope. Starts out really negative, gets less negative. It's 0 at 1. Fermat, we have a minimum. It's positive after that. It gets to be really positive. And then it gets to be less positive until it gets to be 0 again. What's this dot? Where my derivative has a maximum. Wasn't that on the homework questions I just gave back to you? Aha. Same thing here. I have a minimum. So I have another point of inflection, a place where it's 0. And then we get closer and closer to 0, so we start to flatten out. I can do this whole thing visually, the same way we did derivatives. Questions? We did derivatives for motion. I am standing at the top of a tall cliff, and I throw a ball up. Now, for the moment, I've drawn that at an angle. I am strictly thinking of the vertical motion here. So I really should think about sticking my arm over the edge and throwing straight up. Let's change that. We're going to throw it straight up. Two questions. How high does the ball go? And when does it hit the ground? Problem. I don't know squat about an equation of motion regarding this ball, except we're on the earth. There's gravity. Gravity is an acceleration. An acceleration is the second derivative of motion. Aha! Acceleration is the second derivative. Velocity is the first derivative. I apologize in advance. The problem is taken directly from the book, so I'm not using real units. Gravity is 9.8 meters per second squared, damn it. But I'm in feet, so it's 32 feet per second squared. Now I need to make an executive decision. What I've just written is correct if I think of down as the positive direction. If I'm thinking of down as the positive direction, I can use positive 32. It's your call. You get to decide which way is positive and which way is negative. Most of you are looking at me going, that doesn't, no, down is negative. Fine. But if this statement up here, ball is thrown upward at 48 feet per second. If I let gravity be positive, then this number would be negative. You can do it either way. It's your call. But since I see most of you twitching at this, we're going to make it negative. But now, my velocity at time 0 when I threw the ball, that's the derivative of x. And what's more, I know that at time 0, I am at a height of 432 feet up. So it'll be positive. Well, now you can do exactly the same thing we just did. I was given a second derivative. I can take the antiderivative. I'll get the first one. I'll get x prime. I can then solve for the c, because this condition is about x prime. Then I can take the antiderivative again, and I can solve for the height and position function. Now, I have my position function. Let's say we did all this. How do I answer the two questions once I've finished doing my antiderivatives? How do I answer the first question? Find the maximum of h, right? Maximum height, the maximum of x. Finding a maximum means taking the derivative and setting it equal to 0. But I would have the derivative from the velocity equation, right? My ball is going up and then it stops and it comes down. That's where its velocity is 0. Once I know when it happened, because that would give me a time, I could plug that into the height and get how high it is. How do I figure out when it hits the ground? When the height equals 0. When my x of t is 0 again. I could even ask the question, how fast is it going when it hits the ground, right? Because we would have the height and the velocity at a given time. Figure out the time when it hits the ground, plug that into velocity, you tell me how fast it's going when it hits the ground. By the way, it takes about 7 seconds to hit the ground. Little less. It's an ugly decimal. It's quadratic, doesn't have nice roots. But this is real. When am I going to throw something into the air from one height and have it land at another? Oh, I don't know. How about any game that's played on non-level terrain? How about throwing something that's big and heavy that you want to use to knock down a wall? How about launching artillery? People, this is real stuff. I'd love to tell you it was useless, but the defense of Holland with its tiered system of dikes did exactly this. If you came in late, I still have your homework. Please come get it. That's how I'm taking attendance today. This is the last thing that is part of the exam. So Wednesday is question and answer day.